Hey there, folks. Welcome to the last lecture, probably of the semester, on new material. I will go through and do a solution guide to the test. We'll probably do that in class. I'd rather do it like here and then so you have a record of it. We can also spend time in class if that's not sufficient. But I have one new little piece of material that I want to present to you today called the pigeonhole principle. And I debated, the reason I'm so late getting this posted is I was debating what to do with you for our last week here. Thursday's definitely review. But I wanted to cover one little piece of something, and I finally, it occurred to me, like, yeah, you got to talk about this because it really ties together the notion of counting. In a way, it's a counting technique, but then also it's a proving technique. So it actually kind of ties together everything we've done here through the course. So I want to talk about this. Before I do, though, let me just mention this. And I never officially did this, and I guess I just assumed people knew. But one of the things that came out, one of my takeaways from Krista Maxon's talk on Friday, her first talk actually was that students need to be instructed in how to watch lectures when they're a video like this. And it never occurred to me, but I think that's probably true. You're used to watching YouTube videos or whatever it is, and you just watch them. Sit there and look at them. Sometimes pay attention. Sometimes you don't pay that much attention. But when you're watching a lecture over Tegrity or over YouTube, it's very important that you take advantage of the machinery and that you actually take notes. You do more than just passively listen. You actively listen and you take notes. And that's why I'm probably not going to post these notes. I want you to take notes. Now, you have the advantage. Part of the reason I always posted notes was because I didn't want students working so hard at writing stuff down that they couldn't follow what I was doing in class. But with the Tegrity lectures, you can control the speed at which I talk, and I know that some students in the past have watched me at 1.5 speed, and then when something interesting happened or something they wanted to write down, they'd pause it. Or, you can watch me even slower if you want to, but the important thing is that you can pause and rewind, and that's crucial to the note-taking process. It's something you can't do in class. It's something you can do, though, with a Tegrity lecture. And even a YouTube lecture is pause and rewind. And so if I say something and you're trying to write it down and I move on to something too fast that's causing you to have to hustle through there and take bad notes, stop the tape, pause the tape, and write down what you're wanting to write. If something I said didn't make sense to you the first time, rewind it and listen to it again. But it's an active process, and I guess I just assumed that people knew that, but after listening to Dr. Maxon talk, it occurred to me, it's like, you're right. Students are used to just watching, videos of music or, news clips or funny clips, whatever, But you're not used to actively writing things down when you watch those. And so I probably should have, and this is a learning process for me too, but I probably should have given you more instruction at the beginning on how to watch these things and take decent notes. So, the next time I go through this, I will definitely do that early on, but it's never too late to learn something, so let's start now. What I want to introduce to you today is called the pigeonhole principle, and it's remarkably obvious. However, it's remarkably powerful in what it allows us to do. So let me state this for you. If we have in pigeonholes, and this actually, you may guess, applies to more than just pigeons and pigeonholes, but if we have n pigeonholes and n plus 1 pigeons, then at least one pigeonhole will house at least two pigeons. Okay, now very clear why that's true, right? If you, worst case scenario, you've got your end pigeonholes and you've got your first end pigeons, and they all take a hole to themselves, right? Then that end plus first pigeon's got to go in the same hole as one of the previous ones. Okay? Now, as obvious as that sounds, it tells us things. It doesn't tell us, it doesn't tell us how many are in any particular hole, right? It's saying somewhere there, somebody's got to have at least two. Okay? One of those holes has to have at least two. But if I get down to saying, well, how many are in this particular hole right here, it doesn't tell me anything about that. Okay? So we'll look at some examples that that kind of illustrate that. Let's start off with a pretty simple one. Let's say that a drawer sorry, I can't make my W's today for some reason. A drawer, can't write, contains a dozen brown socks and a dozen black socks. All unmatched. So 2 dozen socks total, none connected to any other. So first let me ask this question: how many socks must we take out to be sure that we have at least two of the same color? Okay? Now with this particular example, our pigeonholes are the colors, right? I'm taking out my pigeons here are the socks, and I'm putting them in particular categories. We use pigeonholes and pigeons as the explanation, but really we're looking at things and we're putting them in categories, right? So my two categories here are brown and black. Okay? So these are my pigeonholes, if you will. Now, I could actually reach in there just blindly and get two socks and they're actually the same color. So that's entirely possible, but that's not what we're asking, right? We're saying, how many must we take out to be sure that we have at least two of the same color? Well, worst case scenario here is that I take out two and I get one here and I get one there. Then the next one I draw will be one of the two, and that will give me at least two. So since there's two categories, it's 2 plus 1, 3 socks that I have to take out. Okay? Now, I want to ask you a different question to illustrate when this is not applicable to us. Let me ask a similar but different question. How many socks must we take out to be sure that we have at least two black socks? Okay, now see, that's a different question. I'm no longer asking about the pigeonholes in general, Okay, because what it does give us is a very general statement about, oh, somewhere there I've got a pigeonhole that's got two things in it. But when you start to ask about a particular pigeonhole, then you have to, again, run the worst case scenario, but it's not, we're not using the pigeonhole principle anymore, right? What could happen here, and perhaps it's unlikely, but at least it has a positive probability, is I could take out 12 whole socks, right? And they're all brown. You know, possible. And then to get the other two, that would leave me with nothing but black socks in the drawer, right? And then draw out two of those black socks, and there's my two black socks. So in that case, it's 12 plus 2, 14 socks. But what I want you to notice is that, I guess the reason I give you this example is to point out that, you know, this tells us things about the pigeonholes, you know, in general, but not a specific pigeonhole. Okay, so just an illustration there of when it's useful and when it's not. Okay, now we can generalize this in an obvious way. So let me take this out and let's do what I now call the generalized pigeonhole principle. Says this: if we have n pigeonholes and I'm not going to say n plus 1 now, I'm going to say k pigeons, then at least one pigeonhole will house at least, and I'm going to have to, I meant to actually kind of do this ahead of time, but I'll explain what I'm talking about after I write this. This is new notation to us, although we use something similar. This is ceiling notation, okay? We used floor before, and we've never had an opportunity to use ceiling, but it's the same concept. The ceiling of a real number is the next largest integer. Okay, so I guess I should really say time out here for just a second. And I should go back and describe this. This is a definition. The ceiling, I'd forgotten we hadn't talked about it. The ceiling of a real number x is the integer n such that n is the least integer for which x is less than or equal to n. Okay, so an example would be if I took the ceiling of 1.2. Okay, now we're used to the floor. The floor of that is 1. The ceiling is 2. Okay? The ceiling of a negative now works, you know, that's kind of different in the floor as well, but a negative 1.2, okay, the biggest integer, I'm sorry, the least integer that's bigger than that is a negative 1. Right? If you're thinking about the number line, here's 1 and there's 2, there's 1.2, so there's the next highest integer on this one, Here's a -2, here's a -1, here's a -1.2, so the next one's right there. Okay, but the important thing is that if we do this with an integer, we just get that integer. Okay, just like the floor. Okay, so I'm sorry, actually kind of meant to say this before I started talking about the generalized, but it's an easy concept. What we're saying here is that, okay, and this actually works for n plus 1, right? If k is n plus 1 over n is slightly bigger than 1, so the ceiling of that slightly bigger than 1 would be 2, right? It'd be 1 plus 1 over n, whatever that is, and so the ceiling of that's always 2. So this actually includes the previous pigeonhole principle, but it's generalized, now saying, okay, if we've got so many holes and so many pigeons, then I can tell you that at least one of them is going to have at least that many. Okay, and then, again, this kind of describes the worst case scenario. Let's say we take our n pigeons, or I'm sorry, our k pigeons, and start putting them in the n holes. Okay, if k is bigger than n, then I've got to start doubling up, and let's say I double them all up, and then k is still bigger than 2n. So then I go through and I start putting 1 in each of the others. Okay, this is going to describe this number. Okay. So let's do a problem here. Another example. Time in. So here's an example using the generalized pigeonhole principle in a class of 18 students. What is the least number of students that must make the same grade on an exam? Okay, let's think about that just a second. I've got 5 grades, right? A, B, C, D, F, sorry. A, B, C, D, and F. These are my pigeonholes, right? These are where each student can end up. The 18 students are the pigeons, okay? So the answer here is I've got the 18 divided by the 5 places, the pigeonholes. This is what, 3 and some change? 3 point, and then it's 3/5, so 0.6. Okay, so that is 4. At the very least, I've got 4 students making the same grade on an exam. Now, I can have many, many more than that, right? But if I went through and gave grades by how much I liked you or something like that instead of your actual grade, you know, I could probably distribute. It's like, okay, here's my A, here's my B, here's my B. And I do this with the first 15, so I've got 3 in every category. And then, at the very least, I've got to put the remaining 3 into, separate things. Okay. So on every class, and our class does have 18 students, at least 4 of you will make the same grade on any exam. Okay, and that's an application of the generalized pigeonhole principle. The one thing I do want to show you kind of just on the way out with this, and we'll do just a touch of this in the homework, is that this is so much more than a counting technique. It's actually a powerful proving technique as well that allows us to prove some things that just seem impossible, really, when you think about it. Let me give you an example. Let's show that for every positive integer n, there is a positive multiple of n such that all digits are either zeros or ones. Okay? Now let's stop and think about that. Multiples of n, there's an infinite number of them. Positive multiples of n, right? Whatever n is, I can say 1 times that, 2 times that, 3 times that, 4 times that, and go on forever and ever. So we're taking into account a lot of things. How do I show that each of the digits, and after I, the farther I go, the more digits they have, how on earth do I show that all of those digits are either zeros or ones for some number out there somewhere? Okay? Well, let's think about it. Here's a little trick to kind of show you. Okay, and by the way, this doesn't even give you, this just shows that there's one out there. It's not even maybe the first one, but there's definitely one out there. Okay, and I can show you how to find it. Consider a list of n numbers. 1, 11, 111, 1111, and out here to what this number would have n ones. Okay? Let's think about what happens when I divide these by n. When each of these is divided by n, they each have a remainder that ranges between 0 and n minus 1. Okay, that's actually n remainders, right? Possible. If the remainder is 0, then we are done. We found it, right? We found a number with all ones that is a multiple of n. Okay? If no remainder is 0, then we have n minus 1 possible remainders, and n numbers. Okay? Which means, if you take, I think before we said n pigeonholes and n plus 1 pigeons, but it's the same deal, right? I've got one less pigeonholes than I've got pigeons here. And so, therefore, by the pigeonhole principle, two of the numbers must have the same remainder. Okay? let A and B, with A less than B, they're two of these numbers, and I'm saying A is the lesser of the two, each have the same remainder. Then by the division algorithm, I can write A as N times K plus R, and let's say that same remainder is R. So B then is N times and something else, L, but plus R for some K and L. And now, because these are positive things, these are all natural numbers. Could be 0. Could be 0. Yeah, I should have probably just done non-negative, but that's fine. I'll throw the 0 in there. And K is less than L because A is less than B. Okay? Then here comes the punchline. B minus A would be NL plus R minus NK plus R, quantity. So that's NL minus NK, and the R's just disappear. And this is N times L minus K. Thus, A minus B is a positive multiple of N. And note that if I take one of these lesser numbers and subtract it from the greater number, all it does is just take away those ones over here on the far right. So all I'm left with are ones and zeros. So B minus A has only zeros and ones. And we are done. There you go. Made possible by the pigeonhole principle. So I hope that was a cool example to show you some of the power that we have using that new theorem. Okay, so I'm going to cut you loose. I'm going to let you do a little work here. We're actually working in section 2.3. We're backing up in our book a little bit, but that's fine. And we're going to do problems 1 through 12. And we will take a look at those Tuesday in class. So, and you probably have plenty of time to do them. I'm a little, it's Sunday. I'm sorry, but I was busy with Dr. Maxon all day Friday. And then yesterday I had prior commitments that I had to see to. So it took... Sorry to get to you on Sunday, but I think I've still given you plenty of time, Sunday night, Monday night, to get your homework done. I think you'll find these are interesting little problems. They're fun. And so we'll talk about this. Hopefully I'll have your test grade and back to you on Tuesday. Hopefully I will have already posted solutions to the test, and so if you have questions about that after we do the homework, I can answer them. And then Thursday will be just review for the test, and that's all we'll do. All right, enjoy this, and I will see you later.